Hello, welcome to Processing Motion Part 3. Today's video is on accelerated motion. Acceleration happens anytime you speed up, slow down, or change direction. So if your speed changes or your direction changes, you're accelerating. As a simple example, I have a marble here which is made of uranium glass. Doesn't need to contain uranium. If you drop any glassware, Earth's gravity is going to accelerate it downwards, right? So you got to be careful. That's how stuff gets broken. Other examples, if you're driving in a car, you hit the gas, it can speed up. If you hit the brake, it can slow down. Turn the wheel, it's going to change direction. These are all examples of accelerated motion. So dropping things speeding up, things slowing down. So today we're going to review some of the equations of acceleration, and we're also going to type some computer code that will make objects on our screen kind of speed up or slow down. So let's get started. Okay. So the first thing we want to make note of is to determine change in position. I can do this geometrically by finding the area under a velocity graph. Okay, so imagine we've collected some data and we make a graph, and we have time down here, and let's imagine that we start at a certain velocity, right? So the graph looks like this. So imagine at first we're going at constant speed, and you get this horizontal line here as your graph. Well, to find the area under this, it's pretty straightforward because I just have a rectangle, right? And the area of a rectangle is length times width. So to find delta x in this scenario, all I do is velocity times time, right? But let's imagine a slightly more complicated scenario where the object is speeding up. We'll start in black here. So instead of just remaining at that velocity the entire time, this object has sped up, right, to a new velocity. So let's say it started out at its initial velocity and it's sped up to its final velocity. Well, now we have this extra area up here to account for, right? So in this case, delta x equals the area of this red triangle plus the area of this blue rectangle. So what's the equation of a triangle? 1/2 base times height. So in this case I have 1/2. Base is going to be time, obviously, but the height we need to kind of think about a little bit. The distance between the final velocity and the initial velocity is going to be delta v, right? So draw that a little bit better here. Right, so this distance right here, that height there is delta v. So delta x equals 1/2 delta v times t. Let's stick with our color convention so we can remember what's going on. Plus the blue rectangle, which is v times t. And we're calling this v initial now because the velocity changes. All right, so we have this kind of famous kinematics equation appearing here. We're going to tweak it a little bit, though, so that it looks like the one in our textbook. So what's the definition of acceleration? A equals delta v over t. And if I rearrange this, I get delta v equals a times t, and I can take that and plug it in right there. Okay, so I'm just using the definition of acceleration. Do a little bit of algebra work here by making a substitution, and then we get an equation that looks kind of familiar, right? So delta x equals 1/2 at times t, which t times t is t squared, plus vit. And we can split this delta x up a little bit so that x equals 1/2 at squared plus vit plus x initial, right? Because delta x is x final minus x initial, so if I add x initial to both sides, I end up with this kind of important kinematics equation that looks like the one in our book. And we'll make some computer code using that equation. But before we get there, let's kind of review what's going to happen. I should say preview what's going to happen. So for the first video, we're going to take that equation. Our x equals 1/2 at squared plus v initial t plus x initial. And for our second video, on our second bit of code, when we're using vectors, we will use the definition of acceleration and the definition of velocity. So definition of velocity is change in x over t, and definition of acceleration is change in v over t. Okay, so if we think about velocity as being the amount that the position changes per unit of time, and we think about acceleration being the amount the velocity changes as a unit of time, or per unit of time, we have a kind of a simple system of equations that will sort of guide us, right? So let's get to the code. Okay, so we're going to start by typing out some code using the classic kinematics equation, and by keeping the equations separated out by components. So the x and y component will be thought of kind of separately. So that means we're going to need quite a lot of variables, and then when we switch over to vectors, code will get a lot simpler. So let's define a time variable, because that appears in the equation. The initial x position, the initial y position, the current x position, basically all these are going to have an x and y component. The initial velocity x component, the initial velocity y component, and then we also need to specify the acceleration. This is, after all, an acceleration video. And this is the x component, that's the y component of the acceleration. All right, I believe that's all of our variables. We'll see what happens. We want to avoid setup. I think all we need to do is specify the size of the window we want. This 800 by 600 has been working out fine, so stick with that. And now we want to draw something. So go with 40. We'll draw this thing. I think maybe this will be green or yellow. Probably yellow. We'll see. And then we're going to draw a circle like before in the uniform motion video based on the current X and Y position of the object, and that will be the diameter of the circle. Okay, so now for our fancy equation. The position in the X direction, or along the X-axis, is going to be 0.5, which is 1/2 at squared, so times acceleration x times t squared, which we can just type as times time times time, because time times time is time squared, plus initial vx, which is the initial speed in the x direction, times time, that's not squared, plus the initial x. So that's our kinematics equation there. And we'll mirror that for the y component. The exact same equation, just change your x's to y's. And then, oh, and of course time needs to go up. So each iteration through, we'll add 1 to the time to keep track of that. Close this. And should work. Let's see what happens. Cool. So we've drawn our circle. Everything was initialized at 0, so nothing's going to change yet. So let's go ahead and start moving things around a little bit. So let's move this guy. That may not work yet. Let's move this guy to the middle, and let's give a little bit of acceleration. Because of that time squared variable, acceleration has a pretty big effect, so you want to use a small number here. 0. Start with that. So here we're going to have kind of a ball drop. Cool. And oh, okay. That should have been initial position x at 400. There we go. So you can see it kind of speeding up a little bit. If we increase that to 0.2 or something, it should accelerate pretty rapidly. When you're scaling accelerations, suppose that you're on Earth and things accelerate at 9.8. If you actually type 9.8 into the acceleration, that's a lot of pixels for the given frame rate of the program, which is typically 30 iterations per second. And yeah, it's super fast. You can barely even see it. So sometimes when you're scaling these, it helps just to move the decimal. So maybe try it at 0.98 instead of 9.8. You can see that's pretty good. Maybe 0.098. And there you can kind of see it clearly, right? If I give it a little bit of x acceleration, we can see it kind of moving over that way, right? Or if you're just using, instead of thinking of a ball drop, if you're thinking of, say, a car moving across the screen, something like that, you might want to have it not falling through the air, but driving across the surface of the ground. And then you have something speeding up horizontally, right? So you can tweak all these initial values here and change the accelerations, and it will change what you see on the screen. And this equation kind of allows you to make those changes while not really worrying about the laws of physics, because they're already built into your program. All right, let's try to do this a little bit more efficiently with vectors, right? So we still need to keep track of position and velocity. So let's make a p vector position And for now, we'll start it out at 0. And we need a velocity vector. Start that out at 0. And unlike the uniform motion programming we were doing, now we need an acceleration, because with accelerated motion, you're going to want that vector in there. And that should be it. So let's draw our window. And let's draw our object again. So most of that stuff will be the same, I think, so we can just copy that. And remember, instead of position x, which is the variable we used for the component, we're going to do .x and .y so that our program will extract the x and y position out of our position vector and use those as the position of the circle that we're drawing on the screen. And now we really need to just add the physics in. So position changes at a rate of the velocity. So for every iteration through, we need to add the velocity to the position because that's how much it changes by. So the velocity vector gets added to the position vector. And definition of velocity is, well, definition of acceleration is a change in velocity. So how much does the velocity change by? It changes by the acceleration each time through the code. So this is quite a bit shorter, right? So we've gotten rid of our time variable, which we're just using as iterations through the code, which is inherent in the program. And our vectors kind of combine all of these. So instead of having to specify two separate position component variables, now both of those are embedded in the vector itself. Right, so let's play this and make sure it works. So far, so good. So let's imagine now that we're kind of moving these things around and give it a bit of acceleration to see if we can make this thing fall down the screen. Cool, it works. So now by changing these values, this will change where the object starts on the screen. This will change how fast it's moving initially, and this will change the acceleration both in the y component, in the x component and the y component. So you can do them separately or you can combine them, and we'll look at that a little bit more in depth later. I'm planning to make a projectile motion video, and so we'll be combining those two things together in that video. So last bit of code, let's copy this over to P5 and see if we can't get this thing to work. So remember, immediately change those voids to function, and your size, change it to create canvas. And then our vector notation changes a little bit as well. These guys like to be declared. Within setup. I'm not sure how the global variable thing works with P5 yet, but just by kind of playing around seems to work a lot better in the setup, under setup. And remember, we want to put this dot in front of our variables, in front of our vectors. And you may recall from my previous video that I have no idea why we put this dot, but someday I'll do some research and figure that out. But I'm a practical person, and if it works, it works. So instead of putting new p vector, which you do in processing 3 syntax, we do create vector. I'll leave those alone because that was working before. We can play around with that in just a minute. Background works, fill works, ellipse works. Oh, of course. We've got to add this to everything. Equals, this position equals this dot position dot add this dot velocity. And this dot velocity equals this dot velocity add this dot acceleration. Function, create canvas, adding the this everywhere. Unless I misspelled something, I think it should probably work. Cool, we have an object falling. Although the color changed. That's interesting. So here it's yellow, and here it's pink. Well, that's a battle to figure out a different day. Maybe it's not in RGB mode. It might be in like that hue saturation kind of thing. But regardless, we have something accelerating down the screen. So let's move these around and see, or let's kind of change some of these parameters and make sure the code is responding the way we would kind of expect it to. And no, it's not. Start a new window. I don't have the most recently updated P5, so oh, there we go. Yeah, the color looked right, and then now it's doing what I was expecting it to do. There we go. Now we have a horizontal acceleration. And let's go back to vertical acceleration just to double check and make sure our code is working right. Yeah, there we go. So we can accelerate horizontally, we can accelerate vertically. That all looks great. Not sure what the little glitch was there, but it's working great now. Okay, last thing. Last time I mentioned the book, Nature of Code. If you're a grown-up and you have a real job, I would suggest buying a physical copy. It's on Amazon. You can support Daniel Schiffman's efforts to educate us about processing by paying some money to him. Or if you don't want a physical copy, you can get an ebook. And what's super nice, if you're a kid, you don't have a job, it's available for free online. So he's published it here on natureofcode.com. You can go to all the chapters, all the contents there. He's posted screen caps or screen grabs of some of the code and some of the stuff. And he's also got sort of living code inside the web page. And he posts tons and tons of great stuff. So yeah, check it out, natureofcode.com. and we'll see you next time. Adios.